Hi, everybody. Hope you are awake after a big lunch. I'm going to talk about, my name is Hanan. I'm going to talk about a prediction of events. So many of us know about images, videos, text, time series, tabular data, but apparently much of the data around the world, the important data, I call it, is event data. It could be the time the user decide to churn, the time the user decide to buy, the time a machine is going to break, and so on and so forth. So this is the focus of the talk, is how to predict event data. So first I would like to start with the motivation of the use case I'm going to talk about, which is predictive maintenance, but as I said, it's general for every event. Then I'm going to talk about the wrong way to solve it, about the right way to solve it and result. By the way, I forgot to introduce myself, so my name is Hanan. I'm half a year in Nvidia research. We are doing applied data science for solving network problems. And of course, we are recruiting, otherwise I wouldn't be here. So for motivation, you know, Nvidia is building like huge data centers, like the one that OpenAI is using for train GPT. And the problem with these large systems is that they fail. So here you can see a plot recently published by Mosaic ML, which is a company just bought by Databricks. So they show their training curve, and sometimes there are failures. They show how they mitigate those failures, but it could be great if we could have even predict those failures before they happened. And if you think about it in Nvidia scale, so a typical data center has like millions of parts. You have switches, network appliances, CPUs, GPUs, and so on and so forth. Can you start the timer, please? Thanks. So what is the traditional way to do it? This is how I used to do it. Let's say you want to predict if a customer is going to leave the service, Netflix, or do you want to predict a failure or some kind of event. The typical approach most data scientists use, which I claim is the wrong way, is to use something called box cart model. So you have some box cart that moves around in time, and every time you this is the vertical line is the time of prediction, and the box is your horizon. You say, if there is an event in my horizon, then it's y equals 1. If there is no event, y equals 0. So this is like a classification problem, right? But I'm claiming that this works, right? You can use XGBoost or transformers or whatever you want, but my claim in this talk, like the highlight, is that this framing is wrong. Why is it wrong? It's wrong because first you're losing a lot of data. Let's say you want to predict an event 1 week ahead. I want to know if there's going to be an earthquake a week ahead. So I'm losing the data of my last week. Why? Because all the last week, the labels are not known yet, right? So I have to throw all my most recent data. I have to throw it to the garbage. I cannot train using it because the label is not known yet. It's in data science, it's called sensor data. The data is not known yet. Moreover, the fact that something did not fail does not say that something will not fail forever. It could. We just know, like at this point of time, we just know that this body here, this machine, or this patient has not died yet, but it might die in the future. So we need to consider that our data stops at some time. Last but not least, the width of this box is arbitrary. If we want to have a model that predicts 1 hour ahead, 1 week ahead, 1 month ahead, we need to train 3 models. Or in deep learning, you need to have multi-head, one that predicts 1 hour ahead, one that predicts 1 week ahead, one that predicts 1 month ahead. And it feels like a hacky approach, right? I would like to have a model that I can interview. Say, what is the probability for you to fail in 1 second from now? What is the probability of you to fail in 2 seconds from now? We would like to build a model that we, after the fact, after it was trained, we can ask it question, rather than training it to specific horizon futures. Is this clear? Okay. So what do we want from such a model? So we want many stuff. We want it to support continuous time event. We want it to support telemetry. We wanted to learn temporal patterns and so on and so forth. We wanted to support different type of failure. But the main thing that, as I just mentioned, is that we wanted to support sensor data, meaning we know that we don't know. It's part of the data that we don't know yet when is the machine going to fail. And we want to make flexible predictions, meaning we want to decide what we want to ask after the model was already trained. Who knows this picture? Okay, so this is from 1869. After this talk, you will remember this because it's really interesting. This is the first survival analysis ever been done by a French guy called Mimard. He was a scientist, probably ahead of his time, because this is the first time someone done a survival analysis. So you see in the left is France, on the right is Moscow. This is the amount of people that left France with Napoleon to conquer Russia. And they moved east, they died in battle, and until they went to Moscow and lost. And while running away from the Russian, they kept on dying. Sorry. Okay. And this is the amount of people that returned to France. So it's like hundreds of thousands soldiers went to conquer Russia, and only 10,000 returned. So the take-home message from this is don't conquer Russia. Okay? And this is what survival analysis is all about. So who were here at breakfast time? Okay, so without you knowing, I used the generative AI and computer vision to measure how much you've eaten. I measured how much you've eaten by the type of dessert. So there were fig rolls, chocolate, and crusted creams outside. And from this graph, the survival it means how much was left over time. This is 100%, and over time, things get less and less. So what was the favorite dessert? Fig rolls, because they were eaten or they died in the fastest rate. So this is survival analysis. Now, because it's a data science talk, I want to have equations. So this is a new object called hazard function. What is hazard? Is the probability to die immediately now, given that you have not died yet. But because death is something morbidic, we'll talk about cookies. So think about these cookie monsters, and for it, if a cookie dies, it's terrible. And if they found a new bag of chocolate cookies, and they were really hungry, so they ate a lot, and then they stopped eating, and then they're hungry again, and they start eating again. So the hazard rate was high, then low, then high again. And again, what is the hazard rate? Is this expression, this limit of the probability to die between now and now plus a bit, given that you have not died yet, given that you have not been eaten yet, if it's a cookie. And you can develop that this is actually this ratio where S of t is the survival function, which is 1 minus the CDF. Why am I talking about that? There is a famous distribution called Weibull. And Weibull distribution, it should be as famous as Gaussian distribution. It's very useful. It used to be called in the 50s the universal PDF for scientists and engineers. There was even a paper about stop using Weibull, because it was so popular. So Weibull distribution, you can see it's very similar to exponential distribution, which is like the typical decay that we've learned in school or in a bachelor degree. Think decay exponentially. But there is another factor here, a part of alpha, which is the scaling factor of like how much time does it get to your half-time life. There is also a parameter called beta, which controls the shape. So what does beta do? If beta is smaller than 1, that you are more likely to die when you are young, meaning that you are a cookie that met the cookie monster and it's hungry. So you are more likely to die in the beginning, because then the cookie monster gets full and the probability for you to die later is lower. If beta equals 1, it means that the probability to die is almost the same thing all the time. Okay, it's like some random event. If beta is larger than 1, then as time goes by, you are more likely to fail. Think about a cable in a data center. There are like 200,000 cables in the data center. The older the cable is, the more likely it's to fail. So this is when beta larger than 1. So let's go back to the hazard function. Instead of writing the distribution, I can write a hazard function. And you can see when beta is larger than 1, then the hazard goes up. When beta equals 1, it does not depend on t. And when the beta is lower than 1, then it goes down. I'm almost out of time, so let me go faster. Okay, so we talked about the wrong way, which is classification. What is the right way? The right way is to use a loss function, which takes into account the fact that some of the data is censored. So if I know that there was an event of failure or a cookie being eaten, I would like to increase the probability here. But if there was no event, I don't know when the event will happen, but I know that it will happen after the last timestamp that I have available in the data. So I want to increase the distribution, the probability, or the integral here. So you can write a loss function which describes this. It's like an if statement. If I know the data, then this is my loss. If I don't know when the event is happening, I have a different loss. And the total loss is a combination of both. Depends on whether the data is available or not. Compare this to a cross-entropy loss, it's pretty different. Now you can take R and N and transformers and all the sequential deep learning stuff that you already know, and you can plug the two together. So instead of the neural network to predict whether it's 1 or 0, you make the neural network predict the alpha and the beta of the weighable distribution. So here you can see an animation where the model is trained, and the closest is it to failure, the higher probability for fail is. Okay, so every timestamp, the model outputs alpha and beta. Let's give some interpretation. Every row here is a different engine. This is data from NASA, and here is the time axis. So you can see that this engine died fast, this engine took time to die, and the color code is the value of alpha, which is also the average time to failure. So as time passes, you can see alpha goes down, meaning the failure is sooner and sooner. So this shows that the model works really well because it enables to predict when a failure is going to happen. Of course, in real life, this is the last slide, in real life, stuff are more complicated than the model I've presented because a data center is actually a graph of many objects interacting with each other. So this makes the problem much more difficult. And we also have different type of data. We have log files and time series data and so on and so forth. And last, like I promised, we are hiring, so you can send CVs here. And this is a QR code for this deck, so you can visit it afterwards. Thank you very much.